our special guest is Albert Einstein, who came back all the way from the 1900s.
I'm pleased to be here.
We're glad to have you. Today, Albert is going to tell us about one of his greatest accomplishments, discovering the photoelectric effect in 1905. Could you tell us what the photoelectric effect is?
Photoelectric effect is a phenomenon in which photoelectrons are emitted from a metal surface when light of a certain frequency hits the surface.
I heard about the differing theories of Isaac Newton and Robert Hooke. Could you explain these to us?
Yes, Robert Hooke believed that the photoelectric effect was made up of white wavelengths. Isaac Newton believed that the photoelectric effect was made up of particles.
Awesome. So, Robert Hooke believed that the light came from the wavelengths hitting a prism to create the colors, but Isaac Newton thought that the light was matter and it already had color. So,
Yes, that is true. They did, but believe it or not, both are wrong, since I discovered photons and proved my own theory to be correct.
very cool.
Very cool.
I heard you mention the word photon. Could you define this term for our audience?
A photon is a particle of electromagnetic radiation with no mass that carries a quantum of energy.
Since you have proved all the other theories wrong, could you tell us what your theory is?
Yes. So as I was sitting in my room, I thought, what if it was both? And I conducted several experiments, which turned out to be true. I called it wave packets, which is another word for photons. And yeah.
Now, I'm a little confused on how that works. Could you further explain this to us?
Yes, I actually prepared a diagram for you and the audience, so you can see there. Okay.
Let us show the audience.
Okay, so here's the diagram, very cool. This is what basically Hooke's theory, the waves. This was Newton's theory, particles. And then here's my theory, both waves and particles.
Very interesting. I heard about your quarrel with Robert Millikan. What was the issue between you guys?
So he was basically just trying to prove me wrong, but ironically he ended up proving me right.
Very cool. And now I heard that both you guys ended up winning the Nobel Prize for your ideas for the photoelectric effect, with you winning one in 1921 and Robert Millikan earning one in 1923. I'd like to congratulate you on these awards.
Thank you.
We'd like to thank Albert for coming on our show today.
You're very welcome.
Can we get a round of applause from the audience? Now we're going to cut to Albert Einstein's assistant to give you guys an in-depth look at the photoelectric effect model. Thanks for watching.
The wave model predicts that given enough time, even low frequency light would accumulate and supply enough energy to eject photoelectrons from metal. In reality, metal will not eject photoelectrons below a specific frequency of incident light. The book gives an example of silver needing 1.14 times 10 to the 15th hertz to eject in a photoelectron. Anything lower will not eject one. As you can see, I've pulled up zinc for my example. It's relatively similar. I have silver here, which as you can see is 262 nanometers. And over here it's 300 nanometers. So it's similar enough that I think I can use it. Here's the program I'm using to demonstrate it. So as you can see, it's at a relatively low intensity, but it's still not ejecting anything because it's at 301. So I change this to 30, for example. Or 100, I guess. See? Starting to eject some. If I take it here, not doing anything. If I take it back over here, it starts to eject some photoelectrons. So hopefully that will have helped to explain that a bit more.